Okay, so we have a pretty cool complex integral here today, which is the integral of z cubed times x squared plus y squared over the absolute value of z with respect to z. This is a complex integral, so we have z equating, equating to x plus iy, which is a complex number on the complex plane C, which is equal to this, where the x-axis is x and the y-axis is the y-axis multiplied by I, where I equals the square root of -1, and points are sums between the real and imaginary axes. Okay. So why does all this context help us? Because the absolute value of z is the absolute value of this, and the absolute value of any coordinates will be equal to the distance from the origin of those coordinates. And so therefore, we can have z being equal to the square root of x squared plus y squared. The basic Pythagorean distance formula. Or sorry, Euclidean distance formula. Whoops, camera. Okay, there we go. So now we can say our integral is equal to the integral of z cubed times x squared plus y squared over the square root of x squared plus y squared with respect to z. Now you see that this is the absolute value of z squared. This is the absolute value of z. So now we have the integral of z cubed times the absolute value of z with respect to z. So now where do we go from here? We have a completely complex integral. Do we expand things into real parts? Well, we just took them back, because although we can make this equal to dx plus I times dy, that is pretty lengthy, especially with all our pieces here. So instead, let's look at some other options. We could do the Feynman technique, which is differentiating inside of the integral operator right here, but this function is not holomorphic or analytic, which basically means that it's not complex differentiable. Although it has no singularities or branch cuts, which means that it is continuous and smooth throughout the complex plane C. So, what should we do? This seems like a good option for polar coordinates. So, we have z being equal to the radius times e to the I theta. We have a new formulation for the complex number here, where e to the I theta equals cosine theta plus I sine theta. We can imagine this on another complex plane here, but we then take a circle with radius r and point cosine theta plus I sine theta. You can see now how this originates as a complex number from this formula here, because cosine theta plus I sine theta rotates around the circle, and the radius pushes it outwards or inwards along the complex plane. So this might also make you realize that the absolute value of z is therefore simply equal to the radius, because it is the distance of this complex number here from the origin. So all we have to do is just differentiate z now, differentiate this. So we have partial z with respect to theta, partial derivative with respect to theta, times d theta, because we're using fractional calculus here, just to make it work pretty much. So that's equal to, let's see here, take down the I, because this is the exponential rule of derivatives, so I times r times e to the I theta, d theta comes across. So now we can just plug everything back into the integral. Z cubed, so we distribute the exponent across this new formulation, which would be r cubed times e to the I 3 theta, times r times I r e to the I. R is the absolute value of z. I r e to the I theta, d theta is dz. Now we can take out our constants, I times r to the 5th times the integral of e to the I 4 theta, d theta. Now we have our integral exponential rule here, so instead of multiplying it on the side, we will multiply it on the bottom. Sorry, I'll show you what I mean by it in a second. I time, which is equal to I times r to the 5th, so we multiply our constant part, 4i, down to the bottom, so e to the I 4 theta over 4i, because we're doing reverse. This shows us the fundamental theorem of calculus here too, because we have this taking this I down to the front as a product, but here we're taking the I4 down, or 4i down to the denominator as division. So inverse operations basically is what they're doing there. Don't forget to add a constant. R is equal to the absolute value of z, so we can take out the absolute value of z from that, and we're left with r to the 4th times e to the I 4 theta, which would be z to the 4th using this formula and this piece, and then simplifying our i's, we have 3i on the bottom. Don't forget to add the constant. It's not 0. We don't know what it is because it's an indefinite integral. And we are done.